So today it will be the first lecture in expert system, and we have been talking before about building machine learning models for solving different types of problems. In machine learning, we are working with data, but in expert system, we are working with human experience. When we are working with data, we have lots of data. We need to get more data. We need to have a big amount of data to train our models. We can have videos, we can have text, we can have voice, we can have different types of data, for example, the time series and so on. And some of those data are labeled, some of those data are not labeled. When it's labeled, we can go for supervised learning. When it's unlabeled, we can go for unsupervised learning. Working with data, it's much easier because we develop a pipeline and we can just apply this pipeline to any kind of problems. But before, for example, 20 years before or something, I mean, we didn't have this kind of, I mean, computational resources which we have today, and it was very tough, in fact, to train models because it cost a lot. I mean, you need good computational resources, you need data, but I mean, today it's much easier than before. So at the time, they decided to go for building a system which can solve the problems in a similar way to human. I mean, when someone solves a problem, in fact, he apply a set of rules to this problem. He divides the problem into small pieces, and he try to develop a set of rules, and he uses these rules to solve this problem. So it will be the same. We will try to extract those rules from the domain expert, and we will ask him how he solved the problem. We will have some inputs, as in machine learning also we will have some inputs, we will have some outputs, and in the middle, we will use the rules to infer some solutions. So in this introduction, in fact, it's introduction to knowledge-based intelligent system. What is intelligent machines? What machines can do? For example, history of artificial intelligence, or from dark ages to knowledge-based systems. I mean, these dark ages, it's in fact something very famous in history of machine learning. At the time when they started with a perceptron, for example, they thought that they can build a system, a universal system, which can solve any problem. So from this dark ages, we can go to a very important point. I mean, in artificial intelligence or in machine learning, there's something called strong AI and the weak AI, right? Strong AI, it's a strong AI when we have very well defined problem. When no, it's when we don't have a well defined problem. In fact, we can develop a strong AI. When we have a very well defined problem, which will be applied in another domain, we can have a weak AI. So it will be much easy to solve a problem when you have well-defined problem. It will be simple, just very, very simple. But if you want to develop a system which is universal, which will solve many problems, it will be a really big problem. So the dark ages, at the time, people had very good expectations about machine learning, and they thought that we can build systems to replace humans in many different jobs, for example, and they discovered that it's impossible, in fact. So people get depressed, and people who has been working in this area, they lost lots of governmental funding and stuff like this. They closed lots of projects, and it takes maybe 20 years until they came back again when they discovered error backpropagation. So in fact, when they developed a perceptron, they thought that the perceptron is a system which can be used for solving problems. And this year, in fact, we used a perceptron for solving many problems. So we can use it for solving XOR problems. We can classify iris dataset using a perceptron, for example. We can use it for multi-class classification problems. So it's a very powerful tool. But when they try to use it for solving more complex problems, they failed. So it's very important when you try to apply machine learning or artificial intelligence to define a problem and try to apply it in a very narrow domain. So in this case, you will be able to solve your problem. I don't know why, how can I, okay. So intelligent machines, what machines can do? I mean, it's just philosophy. You can read this. I mean, the definition of artificial intelligence, what machine learning can do, for example, and so on. Um, so I want to. So philosophers have been trying for over 2,000 years to understand and resolve the two big questions of universe. How does a human mind work, and can non-humans have minds? Yes, we can. I mean, we are building machines which have a small mind, which can in fact make some decisions. So we train this small mind to solve problems simple. So for example, we can have cats and dogs. We can build a system which can classify between cats and dogs using using an artificial intelligence system, for example, machine learning, for example, or a neural network. So we can train a model, and this model will have a very small brain, and this brain will make decisions based on perception. So this model will get input from outside world, and he will just try to digest, understand those, and try to map it into some outputs. He will try to make decision and make decisions. This is cat, this is dog, for example. So intelligence, it is the ability to understand and learn things. Intelligence, it is the ability to think and understand instead of doing things by instinct or automatically. Uh, so, uh, so in order to think, someone or something has to have a brain, for example, or which is an organ that enables someone or something to learn and understand things, correct? To solve a problem, to make decisions. We can define intelligence as the ability to learn and understand, to solve problems and to make decisions. And this is what we are doing. Now we are building a system which can learn, correct? I don't know if it can understand or not, right? But it can learn and solve the problems and make decisions. You can say that my system can understand. In fact, if we try to build a system, and maybe the system can evolve with time, so the system can try to learn new skills. For example, I don't know, is it possible or not? So the goal of artificial intelligence is as a science is to make machines do things that would require intelligence if done by humans. We try in another domain, just in another domain, not to try to build a system which will solve, I mean, lots of problems at the same time. It will be impossible. But we can build a system, in fact, which can solve a problem in a very narrow domain. As I mentioned to you, we have cats and dogs, we have iris data set, we have those three different types of flowers, and we need to differentiate between them. It's a hard problem. Maybe you need a professional to do it. For normal person like us, maybe it will be difficult. So now we try to build a system which will behave at the same level of human intelligence, and therefore we call it intelligent system. So he said here it's not simple. We can just say yes and no, correct? So some people are smarter in some ways than others. Sometimes we make very intelligent decisions, but sometimes we also make very silly mistakes. Some of us deal with complex mathematical and engineering problems, but are bad in philosophy and history. For example, some people are good at making money, while others are better at spending it, and so on. So the idea here, in fact, you can build a system. These systems are expecting that these systems will make mistakes. And if you can remember, we plot the confusion matrix, and from this confusion matrix, we know that the system will be confused between 3 and 8, for example, correct? And it's normal because anyone can be confused also between 3 and 8 in some cases. So if when you build a system, this system will be clever in some solving some problems, but also he will do mistakes because human can make mistakes. And in fact, the system learns from human. So in fact, because the data sets which we are using, in fact, someone has been labeling it, for example. So if this person is making mistakes, my model also will be able to make mistakes. In some places, they said that sometimes machine learning is biased against women, correct? It's not biased against women. In fact, it's the data set which has been used for training it is biased against women. So for example, if you are selecting one to take a job, for example, we will collect the data sets from HR companies. They have lots of CVs, and at the end we have decisions, yes and no. So we can build a system to do the same task. I mean, this system will consume lots of data. Maybe it's CVs, informations, and so on, skills, and so on. And the system will match those skills with the skills which from the job, which because we want to match people with a job, for example. So we can build a system to automate this process. And how can we build a system? We will build a system and we will train it using data. And we are collecting those data from people, in fact. So you have HR companies, they have people who are working in this for many years, they have very good experience. So we will collect those data. I mean, one side we have inputs, which will be CVs and skills and interviews and so on. And the other side, decision, yes and no, correct? So if those people were biased against women, for example, so in this case, my system also will be biased because in fact, I'm building a system using the data files which has been collected from human. So if those people were biased, my system also will be biased. If those people make mistakes, silly mistakes, my system also will be able to make silly mistakes. So, but what is the advantage? How can I build a system which is better than each single or each individual person? I can just collect data from different sources. So I can collect Excel sheets from person A, B, C, D, and E. I merge all those data together, and I can train a model using those data. In this case, maybe my system will be much smarter than each individual person. It's the same also when we are building an expert system. We are building the system using rules. We are collecting those rules from domain expert. If you are collecting it from a single person, so maybe your system will behave at the same level of that person. If you want your system to be smarter, in this case, we need to collect data from different sources and merge all those data sources together in one system. So the system will behave at least better than each one of those. One of the most significant papers on machine intelligence, it's called Computing Machinery and Intelligence. It's for Alan Turing. He has, he made a nice movie for him. In fact, he is a very good person. So he has been developing something called the Turing imitation game. And this imitation game, they just try to find a definition for intelligent machine, for example. What is the definition of intelligent machine, or what is the definition of intelligent program, for example. So the imitation game originally included two phases. It has two phases. In the first phase, we have interrogator, a man and a woman are each placed in a separate room. The interrogator objective is to work out who is the man and who is the woman. They just take text, writing to each other, and he asks questions, and he try to differentiate between the man and the woman by asking both of them. So the man will try to deceive the interrogator, and he is a woman, while the woman has tried to convince him that she is a woman. So so this is the situation. The man tried to deceive him, and the woman tried to convince him that she is a woman. So in the second phase of the game, the man is replaced by a computer program to deceive the interrogator as the man did. It would even be programmed to make mistakes and to provide fuzzy answers in the way a human would. If the computer can fool the interrogator as often as the man did, we may say that this computer has passed the intelligent behavior test. So in fact, it was a simple test, and this test was designed to decide if a system is intelligent or not. So, so Turing, he was believing that by the end of 20th century, it would be possible to program a digital computer to play imitation game. Although modern computers still cannot pass the Turing test, it provides basis for verifications and validations of knowledge-based systems. We are doing it in the same way now. When you are developing an algorithm, for example, we try to work with a benchmark problem, because this benchmark problem has been tested with several systems, so you can compare the performance of your systems with other people. We don't need to repeat things, but you can just find the accuracy of your system with the benchmark problems, and you can go to literature review, and you can find that many people has been using the same data set before, and they documented the performance of their algorithms. It make life much easier. So founders of we have some founders of artificial intelligence. McLuch and Bitts. McLuch and Bitts, those are the first founders of, fathers of machine learning, for example. When we are using this, perceptron, it's McLuch and Bitts model, in fact. So this is the first model, which you can call it artificial intelligence. So McLuch created the cornerstone of neural computing and artificial neural network. He developed this artificial neural network in 1943. Newman also, he is in 1930, he joined this Princeton. It's historical stuff. They made something, summer school, and they made a conference or a workshop in 1951, I guess. And from that time, they just said, okay, maybe this is the official birth of artificial intelligence in 1951. So, it's a huge history, in fact, of behind artificial intelligence. But so from 1956 to 1960, it was the rise of artificial intelligence, or the era of great expectations, in fact. So the early work in neural computing and artificial neural network started by McLuch and Bitts was continued. Learning methods were improved. So do you see? Rosenblatt, he provided this perceptron convergence theorem, demonstrating that his learning algorithm could adjust the connection strength of a perceptron. So just as automatic adjustment of the weights of a perceptron, it was a big success, in fact, and a big step. So one of the most ambitious project of the era of great expectations was a general problem solver. This is the problem. Try to avoid this problem all time. So they had a problem in 1950 also. They call it ambitious era or great expectations era, for example. So they try to build a general problem solver. They want to build a system which can just solve any problems, and they have been trying, in fact, very hard. They developed some programming languages and the systems, the platforms, so they can build a system which can just deal with any kind of problems and can solve any problems. And they failed. It was a big fail, in fact. It was a big fail. So when you try to use artificial intelligence and the machine learning optimization algorithm for solving any kind of problem, try to define a very narrow problem and try to apply your system on a very well defined problem. In this case, your chances to solve it will be very high. So I mean, instead of building a system for example, fixing my car, no, I can build a system for checking my tires, for checking my engine, and so on. So you can break down your problem into small pieces, and you can build a system for each small piece. In this case, we can make success. But if you try to build a system which is general problem solver, it will be impossible to make success. I think we can, yes. So in fact, GPS failed to solve complex problems. The program was based on formal logic and could generate an infinite number of possible operators, and the amount of computer time and memory that GPS required to solve real-world problems lead to project being abandoned. So the problem, the building a system, I start with a set of rules. Those rules will generate lots of logics and lots of operators, and rules will generate more rules and so on. So the memory will expand and they will require more time for solving it. So they failed. They couldn't, because they built a system which is continuously, generate more rules. I start with 10 rules, and after 30 minutes, for example, I have 20,000 rules, and number will continue increasing exponentially. So we need memory space, we need computational resources, which does not exist at that time. So it was, important it was impossible to develop this GPS general problem solving. In 1960, AI researcher tried to simulate thinking process by inventing general methods for solving broad classes of problems. So they used the general purpose search mechanism to find solutions of problems. They call it weak methods. We call it weak methods. As I told you, weak methods, it's methods which are developed for solving very well defined problems. We call it weak method. So if you have very small problem you want to solve, and you try to develop AI for solving it in a very narrow domain, you can call it weak method. But if you will go for unsupervised learning, no, it's a strong AI, in fact, right? So it's a trade-off between how much knowledge you have and how much and the complexity of your algorithm, for example. So in 1970, this euphoria about AI was gone, and the most government funding for AI project was cancelled. AI was still relatively new field, academic in nature, with few practical applications apart from playing games. So to the outsiders, the achieved results would be seen as toys, as no AI systems at the time could manage real-world problems. So until 1970, so all those problems which has been developed or algorithms, it has been applied only for very toys problem, very simple problems, and not very practical and not very serious problems. So after that, from 1960 until 1970, they call it this unfulfilled promises or the impact of reality. They promised a lot. When someone study a course, for example, for the first time, he has very big ambitions, and he try to just prove that he can solve many problems, and he give promises, and the problem he will be able to fulfill those promises. So from 1960 to 1970, it was catastrophic period. So difficulties was that AI researchers were developing general methods for broad classes of problems. This is very, very difficult, in fact. They try to develop systems, general problem solvers, for solving very broad classes of problems. In this case, you will fail. You need to define your task, try to make it very narrow as much as possible and clear. In this case, you can just pick any model for solving this problem. In this case, chances will be very, very good, in fact. So early programs contained little or even no knowledge about the problem domain. To solve the programs applied a search strategy by trying out different combinations of small steps until the right one was found. So it's like trial and error effect or heuristic approach. This approach was quite feasible for simple toy problems. I mean, you can use those approach for toy problems because maybe you can try 100 times, 200 times. But when you go to a large scale problem, it will be impossible because you need to try maybe millions and millions of steps, which will take infinite amount of time. So it seemed reasonable that if the programs could be scaled up to solve large problems, they would finally succeed. I mean, they have been solving those toy problems. They have a proof of concept that we can develop an algorithm, for example, for solving a toy problem, for example. So, I mean, in principle, in fact, we have a proof of concept is that we can scale up. When we scale up the problem, it would be possible to find a solution for those problems. But it's impractical because, as I told you, for example, you can claim that you have very multi-objective optimization problem which works fine. So if I want to travel from here, for example, to Amsterdam, for example, I need to buy a flight ticket. I need to have it cheap, correct? And I need to reach my destination very quickly or as fast as possible. So it's multi-objective optimization problem. So you need to, I mean, the customer, he will just search internet quickly and he try to find, he will go for this booking websites, and he will try to search for a cheap ticket. So it's very important to give him an answer within very short time. But if you just claim, okay, I developed a good solution and this solution will give you the best possible solution ever, but it will take 1 hour to solve. It's impractical, correct? We can just say, no, it will take 1 week, but I will give you the cheapest. No one will wait for you, correct? So when you try to scale up your problems, you need to provide solution within feasible time. And it's the same case also. Maybe you are using a quadcopter or an autonomous car, for example, and you have some optimization algorithm. This optimization algorithm will make decision. It will help you to make optimum decision. But at some point, the decision itself is more important than optimum decision. I just need to get some control signal at the moment. I cannot wait, right? So if you have a controller, for example, and this controller uses maybe an optimization algorithm, for example, it's an autonomous car, and I need to turn left now because if I didn't turn left now, I will hit the wall, right? But no, your algorithm insists that he will give you the best possible solution within 2 seconds, 3 seconds, for example. So I need to wait. But if you waited for him, you will hit a wall, you will kill someone, correct? So it's impossible to develop an algorithm for driving an autonomous car which takes that much time. I mean, my calculations should be within nanosecond, for example, right? So and if I cannot get the solution within nanoseconds, right? I will get any solution will be much better than just waiting for the most optimal solution, because at some point I need to turn left and right, for example, and I cannot just continue driving in the same way because maybe I will hit a person, I will hit a car, I will hit a wall, a tree. So sometimes just to narrow down your problem, define your problem very well, put some restrictions to your algorithm. I need to get the solution within this very short time. I don't need to wait. I cannot wait for 2 seconds, for example, because I'm waiting for 2 seconds. My quadcopter will hit a wall or will hit a tree, for example, or something. No, I need to get a decision within this very, very short time. This is the most important for me. So sometimes the most important is a control signal which will come on time instead of just waiting for something which might come after few milliseconds or few seconds, but it's more optimum. It's not important. It will not be important at the time because I will be in the wall anyway. So this is very, very important to understand. So many of the problems that AI tried to solve were too broad and too difficult. People try to build a system, for example, for medical diagnosis. It's very complex problems and it needs huge experience. So in this case, you will fail, right? You don't have enough resources for solving such kind of problem. But we can, as I told you, we can divide it into small problems and build a system for each well-defined problem. So a typical task for early AI was machine translation. For example, they tried to do machine translations in 1950. We have machine translation today, and it's not very accurate, in fact. So, for example, the National Research Council in USA, they funded translation of Russian scientific papers after the launch of the first artificial satellite, Sputnik, in 1957. They want to translate all Russian scientific papers into English because they feel that Russians are ahead and they want to know, what is going on. So they try to build a system, and it was impossible, maybe difficult, to get people to translate those scientific papers, and they want to build a system to make those translations. So initially, the project team tried simply replacing each Russian word with English word. So just like word by word, correct? However, it was soon found that translation requires general understanding of the subject to choose the correct word. This task was too difficult. And in 1966, all translation projects funded by US government were cancelled. It's a problem because if you want to translate something, you need to understand the context, correct? To select the best word, for example. So it's not just word by word. So they have been building this, and they said that we will replace each word, each Russian word by an English word, for example. But of course, it's not correct because we need to know the history, we need to understand the context, and so on. In machine translation, it's sequence to sequence. So if you are studying deep learning, for example, maybe you will do some master degree here, for example, in Olosund, we have very good machine learning course. So in machine translation, it's sequence to sequence. So in fact, the input is a sequence of text and the output is a sequence of text. But I need to keep a history. We can do these translations using models. We call it recurrent neural network. And in this recurrent neural network, it has a memory. And this memory will remember something from the history or from the context of the text which you are translating. This is very important. So machine translation, it's one of the most difficult tasks, even today, in fact. So in 1971, the British government also suspended support for AI research. They appointed a person called James Lighthill, had been commissioned by the Science Research Council of Great Britain to review the current state of AI. He didn't find any major or even significant results from AI research. It was in 1971. He said, no, it's fake. There is no any serious results from AI. And finally, he decided to just, he said, no need, in fact, to have a science which is called artificial intelligence. He said, no, there is no need. It's just fake, correct? We don't need to have a science or a branch called artificial intelligence. So the technology of expert systems, or the key to success, from 1970 to mid 1980, it's the area of key success. So the most important development in 17th was realization that the domain, people realized that the domain for intelligent machines had to be sufficiently restricted. This is very important. We need to be restricted, just don't go for general problem solving. And AI researcher also had believed that clever search algorithm and reasoning techniques could be invented to emulate general human-like problem-solving methods. We need to think, we need to look into ourselves, in fact, how do we solve the problems? And if we can understand how people make decisions, we can build a systems which can emulate the same process and the same approach which people use. So the general purpose search methods could rely on elementary reasoning steps to find complete solutions, and they could use weak knowledge about domain. So this is very important. Weak knowledge. How can we solve a problem with weak knowledge? We don't have all informations, right? We don't have all information about the domain, and we try to solve a problem. And we could, sometimes you want to travel, for example, or go for hiking, and you know nothing. You just know I want to go to that place, but you don't know how can I go there. So you just go outside home, try your bike, for example, try something. So you have weak knowledge about the domain, and you try to collect information all the time, and you can try to make decisions to reach your goal. So when weak methods failed, researchers finally realized that the only way to deliver practical results was to solve typical cases in narrow areas of expertise, making large reasoning steps. So, I mean, this is the conclusion, in fact. If you want to be successful, you need to define your problem very well, and you need to solve your problem in a narrow, very narrow areas of expertise. So I cannot build a system which will replace doctors, but I can build a system which will assist them, for example, to diagnose some skin disease, right? Something simple, but not general purpose system which can be replaced in doctors in hospitals.
So can I just ask
Yeah.
quickly?
Yes.
So the point of these, or have you actually gotten into expert systems yet, or is this just the build up to them?
Yes, it's a history, but we will build our own expert system. In fact, we will build
Yeah.
it from scratch.
But so the idea then is that the expert system will be fully constructed as opposed to the training done with artificial neural networks. It's fully constructed and made using primarily a result desired rather than the process.
No, it's the process. In fact, we will try to extract some rules from the process, and we will use this one to apply it to the data, right? So we're not working with the results. In machine learning, we are working with labeled data, for example. So I already have some X values and I have some Y values labels, and I will use those input-output relationship to build a system which will try to mimic or understand the mapping between inputs and outputs. But in case of expert system, I will ask you, for example, how do you, for example, cook, pizza, for example. So we'll say, okay, to make pizza, we have those steps. 1, 2, 3, 4, 5. Correct? So if I have cheese, for example, and if I have tomato, for example, if I have something, I will make this kind of pizza. If I have, uh, I mean, so other things, for example, I will do this and I will do that. So you will look into the resources which you have and you will decide what type of pizza should we make, for example. I will look into my fridge and I will decide what kind of pizza which I can do, for example, using the materials which we have at our fridge.
But an
So
expert system is still a kind of classifier, is that right?
yes, we can use it for classification. We can use it also for regression, right?
Okay.
So it's the same, because if you go to the bank, for example, and I want to get a loan, maybe the guy in the bank, he will just say, no, we will, for example, I want to open bank account. So the decision will be yes and no. So they need to check my background and stuff like this and allow me if I should have a bank account or not. So this is yes and no. So some domain expert can make this decision. So it's the same also. If I want to get a loan, I apply for 5 million and they will say, no, you cannot get 5 million, you will get 3 millions. So it's a regression, correct? So in fact, I can use expert system for making, it's the same as artificial intelligence, as machine learning. I can use it for making decisions, for classifications, and I can use it also for regression. So we can build the systems. I mean, we will try to build systems. We will try to find rules also and build systems for solving many different problems. But expert system, it's based on human experience, not data, in fact. So if you want to build a machine learning, I need to go to the bank and I need to collect Excel sheets. Those Excel sheets, they include all information, the customer information, for example, names, age, income, and so on. And the last column, for example, which is a target, maybe it's the loan which they will get, correct? So it's a regression problem now. I have inputs and I have outputs. Outputs are numerical values, not decisions, not 1 and 0. So in this case, I need to build a system which can make this regression process. So I can build a machine learning for doing it because we have data files. If you don't have files, but I have the people who are working in the bank, so I can ask them, how did you classify this customer that he should get 2.5 million? They will say, okay, because his income is in this range, because his age is below this one, because he's, living in Oloson, for example, because he is a Norwegian citizen. So in this case, we will give him this kind of loan, for example. So there are many steps. I need to extract this knowledge from the domain expert and try to implement it in my system. So my system at the end, I will have a knowledge based and I will have inference engine. This inference engine will use the rules from the rule base and it will try to make decisions. It will apply those rules to the inputs. If you have a new customer, for example, so we will check his age, his income, and so on. And and we will make decision how much he should get, for example, or if we should give him a bank account or not. So in fact, expert system, it's about human experience, and those human experience will try to extract it as a set of rules. And when you have many rules, your system will be smarter. And it's similar. Like in machine learning, I can build a machine learning using 200 examples. So it will have this kind of accuracy. Maybe the accuracy will be 70%, but if I trained my model with 10 million images, it will be much smarter, like AlexNet. So AlexNet, for example, it's a neural network which has been trained to detect objects and identify objects from images. They have been training it using millions and millions of images. So AlexNet is very, very, very smart. If you give it any image, it will be able to classify how many items in the image and what is each item. This is cup, this is keyboard, this is computer. It will be able to identify any object in an image. It's really very smart because we trained it with millions and millions of images. But in expert system, if you build a system with 10 rules, it will have this kind of accuracy, for example. But maybe in the future, I will get a case which is really very difficult. So maybe if I have more rules, I will be able to cover also this one, and I will be able to find a solution for it. So when you have many rules, your system will be smarter. And remember, we get those rules from domain expert. So I can go to the bank and I can meet, for example, 10 people working in the bank. If each one will give me 10 rules which he is using, for example, so at the end, my system will have 100 rules. And then when we try to solve a problem, we will apply those 100 rules to the input, and then we will make decisions. So we should expect that my system will be smarter than each single person in the bank.
But you've still put in all of those 100 rules manually.
Yes,
like
manually.
you as the creator, you make those rules.
Yes.
And then you get essentially just a function out, and you put that in.
This is correct. This is totally correct. So we get those rules manually, and we implement it like hard coded in the system, right? I will show you later on. And the system it's based. We build the system manually, in fact, and this is the problem here, because when it's based when you build a system manually, it will be very expensive to maintain it. Because if I need to build the system or tune those models or check which model is working, which model is not functioning anymore, so it's a really very expensive task, especially if your system is very complex. So imagine that your system has millions of rules, for example. So it would be very hard to go to those set of rules in a rule base, for example, or a database, and to find out which rule was working, which rule is not working, which one we need to update, right? Because if I build a system from 1980 in a bank, for example, to give people loans, for example, maybe the system will not work today because the income is different. Prices of houses are different, right? So if I will use a system from 1980 and I want to apply for a loan, for example, 5 millions, maybe he will just say, no, it's crazy. We will give him 500,000 because in 1980, 500,000, you can buy a house. Today, you cannot buy anything, correct? So because we build a system using the knowledge of the people who have been living in 1980, I cannot use the system today, right? So this is a problem. I need to update my systems, and if you want to update your system, it will cost you a lot. And this is the advantage of working with data. But if you are building a similar machine learning model, which has been trained using data, no, it's easy because I can just collect the data from last year, for example, and I can just retrain my model and it will work perfect. So imagine I build a system in Oslo and they want to use it in Oslo, in Olesund, for example. I will just import the system. I will collect some data from Oslo, Olesund, and I will retrain the model one more time. So the system will work fine. But if we build a system, for example, we are building a system for diseases and diagnosis, medical diagnosis, and we build it using experience from doctors who has been working in Olesund Hospital from 1980 to 1985. So imagine, I want to use the system today. Do you think this system will be able to discover corona, for example? It will not be able because this disease, it's a new disease, for example, and there are lots of diseases, correct? And those antibiotics, it's different antibiotics, different prescriptions, and so on, different medical symptoms. And so the situation will be totally different. The system which has been developed in 1980, maybe I can use it until 1985. But after that, it will be impossible. Because if you can look around you at the time, maybe the people who has been helping you, they have been retired, in fact. They are not in work anymore. So the system will be outdated, and we need to update our system If I need to update my system, I need to go back to the hospital. I need to sit down with the new doctors, right? Who got their fresh educations and lots of experience. And we need to go through those rules, and we need to try to select which one is working, which one is not working, which one we need to update, which one we need to fix, and so on. So it will be really, really very expensive and very costly. So working with expert system, it's very tough, and it's not flexible. In fact, compared to machine learning, it's not flexible, not easy to use. But at some point, it was very good in 1980, 1990. It was very, very good. But today, maybe it's not that. I mean, it's not very exciting. In fact, building.
So really, it's an archaic method that's not really. It's not used much anymore, I suppose.
Yes, correct. It's not used that much, in fact. But there is a trend. In fact, I mean, we are studying it because this expert system, it's white box, right? We have been working with artificial neural network. Artificial neural network, it's a black box models. When it's a black box models, it will make decisions, and it will not help us to understand how decision has been taken. So if you have a patient, he has symptoms, and the system said, okay, he has corona, for example. It will not explain to you why he has corona. Maybe he has symptoms like corona, for example, and the system will say, no, it's common cold. It's not corona, it's common cold. Maybe if you are a doctor working in a hospital, you want to understand why. I feel that it's a corona, but the system said, no, it's common cold. Maybe the system is correct, right? But we need to understand why, right? Because this is a patient, this is a doctor, and he want to write a subscription. I mean, he want to give him a medicine, for example. He want to be convinced, and the patient also, he want to be convinced, right? So you need to explain to him why it's not corona and it's just common cold, right? So if you are using machine learning, this decision making, it's hidden. It will just say, no, it's common cold, but it will not explain why it's common cold. So if you have two cases which are very close to each other, like common cold and the corona, for example, and it's almost the same symptoms, but if it's corona, it's dangerous. He should stay at home, correct? And he should take some special medicine or something, or right? We need to take care of him. But if it's common cold, it's okay. You will be fine after 6-7 days without any medicine, correct? But symptoms are the same. So if you have a system which will decide, okay, this is common cold and not corona, in this time, people will be very skeptical and they'll say, no, we don't trust the system because we will not take the risk because they don't understand. But if you can show them why the system has decided that this one, it's a corona, it's common cold, for example, they will be convinced and they will say, nay, yes, we accept this. So when you are using machine learning in such area, complex area, in medical domain and stuff like this, when it's something related to our life, people need to understand. If it is black box model, people will not be able to understand anything, because when you open a machine learning model, you will just have a bunch of numbers, lots of weights, numbers, and that is it. You apply all images and all CT scans and MRI images and blood analysis and so on, and the system will say, okay, this is common cold with probability 95%, for example. But if the doctor and the patient feel that it's something very close to corona symptoms, maybe he will say, no, I don't trust it, I cannot accept this, correct? So if it is black box model, you will not get this explanation. But if it is white box model, we have explanation facilities. Those expert systems, they have explanation facilities. So to explain, it's because temperature is in this range, for example, because his pressure, whatever, all those symptoms in this range. So this is common cold and it's not corona. So it will give you a report, in fact. So in expert system, when you made a decision, you will get a report. By reading this report, you will accept the decision. You will understand why it's common cold and not something else. So expert system, it's white box system. When it's white box, it has an explanation facility, and it will be easy for us to understand how the decision has been taken. So this is the difference between black box models and white box models. So the trend today, in fact, is to reinvent and try to develop those expert systems, because we still need those expert systems. And at least now, as I told you, we are building those systems based on rules, and we are getting those rules from the domain expert. We can also extract those rules from data, and this is a good news, in fact. So if you have also Excel sheets, we can, from those Excel sheets, we can try to extract rules from the data, use these rules in the system, so the system will be able to learn from data and at the same time will be still white box, right? Because in fact, in the machine learning, so for example, if I have an image and the image it's cat, and the system will decide, the machine learning model will say, okay, this is cat. In fact, we try to build this rule or mapping between inputs and outputs. So we will have anyway, we will have a kind of rule which will use the input image and it will decide that this one it's cat or dog. But it's not I mean obvious, not something which we can feel, but I mean indeed it's a rule. They try to develop a rule, and this rule will be applied to the input image to make a decision. So we will get those rules in a way, but it will not be explicit, in fact. But in case of expert systems, we will have a set of rules. When we apply an input values, some of those rules will be fired, and this process they will go this process until decision making. So we can trace back, in fact, and we can find which rules has been fired, and we can get a nice report describing why this patient has a common cold and not corona, for example. And it's the same in many areas also. So for example, if you go to the bank, I want to get a loan from the bank, and they said, no, you cannot get a loan. If they didn't provide answer to you, answer which can convince you that it's no because of this and that, I guess they will lose a customer, right? They will lose a customer, and maybe they will lose a good customer. Because if they can give you an explanation, maybe you can discuss with them, you can adjust your numbers so you can get your loan, right? But if it's black box models, it's just a black and white. No means no, right? No explanation, we don't know. But it's just no, the decision is no. You will feel that those people are very, really not, maybe not political, and you will feel maybe abused or something, and you say, okay, I will not go to this bank again. So you are losing the customers. So to explain how decision making is done, very, very important in many domains. So maybe in the media, you feel that those systems are not hot enough as machine learning, but those systems are still important, in fact. As an example, there is a field called search and rescue, for example, in Norway, for example. So search and rescue, someone is lost, and they try to search for him until they find him. They open a case when someone is lost, and then when they find him, they have documentations of the whole case, and they close the case, right? So in fact, they have lots of cases. So now we are working with rule-based system. We can work also with a different type of expert system, which is called the case-based reasoning. Case-based reasoning, I have cases. Those cases are knowledge. And for example, if I have someone lost today, for example, one easy approach is to try to find similarity between his case and the other cases, and you can find the case which is closer to him, and you can follow the same approach which has been used in this search operation, right? To apply it for him, to find him quickly, for example. So it's also case-based reasoning. So in fact, expert system, there are two types, one called rule-based system and one called case-based reasoning. In rule-based reasoning, we work with rules. We extract those rules from the domain expert. In case of case-based reasoning, we have a case. Each person will be a case. So for example, there is a bank, and the bank has 100 customers. Those 100 customers, they apply for a loan, for example. So each one will be a case. So if you have new one applying for a loan, we can try to find the one which is closer to him, right? And we can just maybe treat him in the same way. So they call it case-based reasoning. So we have rule-based reasoning, we have case-based reasoning. Those approaches are not very hot, correct, today, but it's still important. It's still very, very important, because we have white box and black box models. Explainable AI. What is explainable AI? Explainable AI, it's the AI which will allow you to understand how the decision has been done. This is very, very important. So they have been developing lots of systems and platforms for expert system. So just as an example, for example, Dendral, it was a system developed at Stanford University, and also Mycene, a role-based expert system for diagnosis of infectious blood diseases. So it provides doctors with therapeutic advice in convenient, user-friendly manner. So those systems are using in hospitals, and it's based in role-based systems. Prospector. Prospector was an expert system for mineral exploration developed by Stanford Research Institute. So you will give, you will give this system some analysis and some geological factors and stuff like this, and he will just make some decisions about the deposit, mineral deposit. So, however, expert systems are restricted to a very narrow domain of expertise. It's restricted to a very narrow domain of expertise. For example, Mycene, which was developed for diagnosis of infectious blood diseases, lacks any real knowledge of human physiology, for example. So if a patient has more than one disease, we cannot rely on Mycene, for example. It does not have this capacity, in fact. So if you have a patient which has two diseases at the same time, Mycene will not be able to discover this. So prescribed for the blood disease might even be harmful because of the other disease. So maybe he will give you a description, right? But it will be very dangerous because he didn't consider other symptoms and other disease. So expert systems, you can choose a sequence of rules they apply to reach a solution. This is very important. This is what we call it explanation facility. So the expert system can show the sequence of rules they apply to reach a solution, but cannot relate accumulated heuristic knowledge to any deeper understanding of the problem domain. He will show you the steps. To make this decision, we followed those steps. But of course, he will not, show any deeper understanding of the problem domain. Expert systems have difficulty in recognizing the domain boundaries when given a task different from the typical problems. So an expert system might attempt to solve it and fail in rather unpredictable ways. Heuristic rules represent knowledge in abstract form and lack even basic understanding of the domain area. I mean, there are lots of pros and cons. How to make machine learning or repairs of neural network. So in mid-18s, researchers, engineers, and experts found that building an expert system requires much more than just buying a reasoning system or expert system shell and putting enough rules in it. So it's not only, in fact, because if you want to build a system, an expert system, we need to buy this, they call it expert system shell or reasoning system or reasoning engine, for example, and we need to put some rules in it. So in this case, we can solve any kind of problem. So this, at that time, researchers, they decided to have a new look at neural network. By 60s, most of the basic ideas and the concept necessary for neural computing had already been formulated. However, only in the mid-80s did the solution emerge. So the major reason for the delay was technological. There was no PCs or powerful workstations to model and experiment with artificial neural networks. So in fact, they developed all formulations and equations and stuff like this, but they waited until 1980 until computers has been developed. So in 1980, because of the need for brain-like information processing, as well as advances in computer technology and the progress in neuroscience, the field of neural network experienced dramatic development. Major distributions to contribution to both theory and design were made on several fronts. So they started by this hope-filled neural network, self-organizing maps, reinforcement learning, backpropagation learning algorithm. It was in 1986. So have been studying in error backpropagation. Error backpropagation is very, very important. Without error backpropagation, we will not be able to train feed-forward neural network and even deep learning network. So it was first introduced by Bryson and Hu in 1968. So artificial neural network have come a long way from the early models of McLeish and Pitts to an interdisciplinary subject with roots in neuroscience, psychology, physiology, mathematics, engineering. Yeah. So after that, because this book, it's about, in fact, it's about artificial intelligence, about expert system, about artificial neural network, about genetic algorithm. So also we will talk about biological systems, how living systems are propelled toward high-level intelligence. It's evolutionary computation, in fact. So there is something called the genetic algorithm and genetic programming, for example. I mean, genetic algorithm, you can use it for solving very complex problems, optimization problems. So the concept of genetic algorithms was introduced by John Holland in early 17s. He developed the algorithm for manipulating artificial chromosomes. We have a chromosome. The chromosome, in fact, it's a string of binary digits, and it uses some genetic operations such as selection, crossover, mutation. So the genetic algorithms are based on solid theoretical foundations of the schema theorem. So genetic programming represents an application of the genetic model of learning to programming. Genetic programming generates computer programs as a solution. I mean, in genetic algorithm, you can use it for solving really very complex optimization problem. It could be single or multi-objective optimization problems, but genetic programming, in fact, we can use it for writing an equation. So imagine you have, do you know x squared, right? Function called x squared. So if you can plot x squared, for example, you have a set of data, and we want to find an equation to represent this data, for example, fitting an equation to the data, for example. So we can use genetic programming for doing it. Computing with words. I mean, fuzzy rule-based expert systems. They call it computing with words. So in fact, we can divide the system. It has been invented by Lofizada. And it has been used for the first time, in fact, in Japan in 1980 something, 86 or 85. So fuzzy rule-based system perform faster than conventional expert system. I mean, we have this expert system shell. They have been developing those softwares and the platforms for developing expert systems. So they build this expert system shell. It was expensive, and you need to buy it. And after that, you need to extract your rules from the domain expert and try to implement it in your system. So now your system can work. But fuzzy, I mean, Zada, in fact, he developed a system which anyone can build. In fact, we don't need to buy those platforms. We don't need to learn very complex programming languages, but we can just know some basic stuff to build our expert system using fuzzy logic system. We will be building it here also using fuzzy logic system. So fuzzy expert system merges the rules, making them more powerful. And Lofizada believes that a few years, the most expert systems will use fuzzy logic to solve highly nonlinear and computationally difficult problems. Conventional expert systems are built for a narrow domain. It makes the system performance fully dependent on the right choice of experts. When a more complex expert system is being built, or when expertise is not well defined, multiple experts might be needed. However, multiple experts seldom reach close agreements. I mean, there are some conflict between different peoples, and there are often differences in opinions and even conflicts. This is especially true in areas such as business and management, where no simple solution exists and conflicting views should be taken into account. So fuzzy expert system can help to represent expertise of multiple experts when they have opposite views. It's why, because the system will consist of in fact will consist of number of rules, and we can have a weight value for each rule, for example. So if I have multiple experts who are providing those rules for us, we can differentiate between those rules with certain techniques. So fuzzy systems allow expression of expert knowledge in more natural way. They still depend on the rules extracted from the experts, and thus might be smarter or dumb. Correct? Might be smarter or more stupid. I mean, some experts can provide very clever fuzzy rules, but some can just guess, and they may even get them wrong. So all rules must be tested and tuned, which can be prolonged and tedious process. For example, it took Hitachi engineers several years to test and tune only 54 fuzzy rules to guide Sendai subway system. I mean, in Japan, they have a fuzzy logic system, which is, I mean, managing a subway system in Japan, and the system consists of 54 fuzzy rules. And it takes many years from the company to try to test and tune those small set of rules. So in recent years, several methods based on neural network technology have been used to search numerical data for fuzzy rules, or change and tune existing ones based on the data provided in other. So to summarize this one, expert, neural, and fuzzy. I mean, we finished the neural network. And we will build expert system using fuzzy logic systems have now matured and been applied to a broad range of different problems, mainly in engineering, medicine, finance, business, and management. And each technology handles the uncertainty and the ambiguity of human knowledge in a different way, and each technology has found its place in knowledge engineering. So in fact, they are complementing each other and they are not competing with each other. This is very, very important. The synergy of expert system with fuzzy logic and neural computing improves adaptability, robustness, fault tolerance, and the speed of knowledge-based systems. Besides, computing with words makes them more human because in fuzzy logic system, we can just use words instead of measure things. So for example, if you are talking about temperature, we can just say it's hot and cold. If you are talking about tallness, we can say someone is tall, medium, and short. So we're computing with words, we are using words, human words, which makes it easy for us to understand. Because also it's important because when we use rules, we are extracting those rules from human. So those rules, in fact, it's just if-then rules using our daily language, and also the variables here also will be words.
So, question about the fuzzy part of the logic.
Yes.
How would that actually work in practice? Let's say that you're building a system for finding what kind of clothes someone might wear.
Yes.
So you have an input for height, short, medium, and tall, and you have an input for build, slim, medium, and large.
Yes.
And how would that work? Would you then translate the fuzzy input into some numerical value, do some work on it, and then translate it into something fuzzy output?
Yes,
Or how does it work?
This is very good, very good. We have something called fuzzifications and defuzzifications. So first, we will make a simple example. So imagine it's I mean, I want to wear today, for example, heavy clothes or light clothes because the temperature it's as you can see it right now, right? So first I need to translate those I mean weather condition or temperature into word. So I can just say it's cold, very cold, medium, warm, for example, right? I can say it's cold, correct? I can say it's cold, medium, and warm, right? So I can fuzzify, I can represent temperature outside with those three words. When it's cold, in the middle we have medium, and when it's hot. So cold, medium, hot. And I want to decide what kind of clothes should I wear today, for example. So first, what is cold? I can say that cold, it's a temperature between maybe cold between maybe it's between 5 and 15, for example. So 5 and 15, it will be cold, right? What is medium? Medium, maybe it's something between 10 and 20. It will be medium. Hot, maybe it's something between 15 and 25, right? So when you measure temperature outside, I need to convert it into this one of those three words. We call it fuzzification. So I will measure temperature. Maybe it's now, it's maybe it's 20, for example. So maybe it's something between warm and between medium and warm. Or I can just say it's warm. Imagine it's 25, so it's warm. So if temperature is warm, what kind of clothes I should? If temperature is warm, so clothes is maybe light, right? Not warm clothes. It's just a normal or light clothes. So I will build my rules. When you go outside, what kind of clothes? I mean, you just check temperature before going out, and then when it's cold, you will just wear very heavy jackets. So in fact, you make decision based on the temperature outside. And if we need to convert this one into fuzzy numbers, we need to fuzzify first temperature, outside temperature. Outside temperature, it's just something which we can measure. So we need to convert it into a fuzzy word. So we will decide how many words we need to represent the temperature. So we can just say, okay, it will be, for example, cold, medium, and hot. Cold, medium, and hot. When it's hot, I wear heavy clothes, light clothes, for example. When it's cold, I mean something heavy, correct? When it's medium, it's something medium, right? So I can build set of rules. It will be three rules, right? If temperature is hot, clothes is light, right? If temperature is medium, close is medium. If temperature is cold, so close is heavy, right? So now I have 3 rules. So now you can just draw the system. We have 3 inputs, and we have 1 input, and we have 3 rules. So I will measure temperature, and I will convert it into one of those 3 levels. So if temperature is hot, so only 1 rule will be fired, right? So when this rule will be fired, the decision will be, okay, you need to wear something light because the temperature is warm, right? Or hot. So we will apply the input. We have the input. First, we will measure the temperature outside. We will convert this temperature into one of those 3 words, correct? So now I converted into hot. So now the input to my system will be hot. So 1 rule will be fired because I have, if temperature is hot, cold, medium, so the first rule will be fired. When it's fired, it will infer the output. What will be the output? Close is, for example, heavy because it's cold. So 1 rule will be fired, and when this rule will be fired, I will get some decision or some output. Just as this very simple example. So you are correct. First, we need to measure the temperature outside, and the temperature will be numerical value. We need to convert all numerical value into words. This process, we call it fuzzification. We call this fuzzifications. And after that, I will apply this input to my rule base. Some of those rules will be fired, and when it's fired, it will infer something. It will infer output, right? So the output will be close is heavy, for example. So this one will be my output. What is heavy? I need to look into my clothes, for example, at home. Maybe you are dividing it, and this one is heavy, this one is medium, this one light. So I will pick this one. I will pick this heavy jacket because it's cold outside. So now this is a decision making. Very, very simple example. Is it clear, Magnus?
Yeah, I think so. But do I understand right in that since the input is fuzzy, that would also somewhat account for more variability? Like, let's say that I am more cold tolerant and less heat tolerant than you are. So for me, maybe cold is between -20 and -10.
Yeah.
Then I would be wearing colder clothes than you, even if I say that it's warm or cold or medium.
Yeah,
right?
you are very good. You are very good, Magnus. In fact, you are very good. I mean, you are very progressive. So, because we will talk about this later. I mean, working with fuzzy logic system, we have a kind of uncertainty because my hot is different from your hot, correct? So we will represent it using a fuzzy set. We will represent, I mean, this hot and cold, we will represent it using fuzzy set. And this fuzzy set, it could be just single line if people are, for example, people who are living, all people who are living maybe in Norway, for example, they have the same feeling. It's cold for me, it's cold for you, because all of us, we have been born here, we have been living here, so we have the same culture, the same feeling. So your hot will be the same. What is meant hot for the rest of your family. All people agree on this, correct? So in this case, we will represent this fuzzy set with a single line, right? But if we are talking about you and someone else who is living in South Africa or Middle Africa, for example, you're hot here. I mean, when it's in Norway 20, 22, it's hot in Norway. But when it's 22 in some other places, in fact, it's cold. And people wear heavy jackets. I know in some places when it's 25, wow, it's freezing. It's very cold, right? So this is a difference, in fact, or at least my hot is different than your hot. Maybe it's hot for you, but it's very hot for me, correct? So when you go, for example, to Egypt, for example, in summertime, it's 45. So it's burning, and you know, for you it's crazy. You cannot afford it. But for other people, no, it's hot. It's just hot. It's hot, not very hot. It's just hot. But for you, it will be very, very hot, right? So in fact, also in fuzzy logic system, we have something called hedges. We use those hedges to represent very, for example. So I can just I can convert the fuzzy set which called hot into very hot and very, very hot, right? And for the uncertainty, because maybe you, I mean, there is some little difference between you and maybe your colleague in the same classroom. I mean, you feel it's hot, and you feel no, it's okay, right? So this is uncertainty, in fact, because the range will be different. For you, hot, it's a number between 10 and 20. For someone else, no, it's not 10 and 20. I feel it's 8 and 18, for example, right? So do you see the difference? It will be 2 degrees from this side and 2 degrees from this side. So we will use those 2 degrees to create a fuzzy set with a thickness, correct? So I will build a fuzzy set with a thickness to represent each temperature, or to represent variations or uncertainty, in fact, right? To try to build a general system which can satisfy all people, in fact. It's a way to build a system which will satisfy all people, because when we build a system, we don't need to build a system which is customized for a single person, but I can build the air conditioner which will be okay for all people at the home, for example, right? Even if there is some tolerance, some difference between each one who is living in the same house. So for example, we are living in the same house, and we will just adjust the air conditioner at medium, for example, right? So if I made it medium for you, which is medium for you, but for other people, no, it's hot. So people will not feel comfortable, and it will be a problem. My product will fail, in fact. So in this case, we can try to collect knowledge from different people, and we can try to design a fuzzy set which can consider tolerance or uncertainty between people, right? Different in opinions, because I mean we are human, and there is difference in opinions between all people, for example. So from my point of view, when I eat something, for example, I feel no, it's disgusting. Someone else will know it's delicious, right? So there's some difference. We try to combine all those knowledge, right? All those I mean difference between individuals, and try to build a general fuzzy set which can accommodate, which can consider those small differences between people. We call it uncertainty, in fact. Fuzzy logic system is brilliant in dealing with uncertainty. We will take more examples in the future, but I'm happy because really you are, I mean, very progressive, and try to ask about points which are very important. We will deal with this. We will deal with this, I mean, maybe in the next week. So, I mean, the rest of today, it's just the tables, making some comparisons. So it's just an introduction, in fact, today to fuzzy logic system. The most important when we implement it. I mean, the most important, in fact, when we implement fuzzy logic system. So maybe next week we can start implementing some functions. So I will introduce the whole system, the block diagram of the whole system, for example. So we have those functions 1, 2, 3, 4, 5, and we need to implement each function step by step. So this is what we will do next week. So we will explain each function of the fuzzy logic system. We have fuzzifications at the beginning, and in the other side, in the output, we have defuzzification. Because fuzzy logic system, do you remember when we have been talking about neural network? Neural network works with numbers. So when we are working with image, in fact, we are working with pixel value, and the pixel value is a number. Even when you have some categorical variable, for example, I have a data, and the data is male and female, for example. So I have a data set of customers, and those customers, they are classified into male and female. No, I cannot work with male and female. I need to convert it into, for example, 1 and 0, 1 and -1. So I need to convert it into a number. It's the same also. We try to differentiate between some objects. So object is, this is a TV, this is cup, this is computer, for example. No, we need to replace it with a number. Text, when we are working with text, we need to use word embedding, because text is text. If I need to build a system for machine translation, in fact, in the machine translation, it doesn't know anything about each word and each sentence. We convert all words into numbers, right? And we will have a sequence of array of numbers input, and the output will be an array of numbers. And after that, you will pick the index of each word. So we will make this machine translation, in fact. So machine translation, in fact, they are not working with text at all. I mean, inside the machine learning, they are working with numbers. So when you are building a chatbot, for example, and I just say, how are you to the chatbot? So the chatbot should understand that I'm greeting him, and he should be, oh, how are you, Ibrahim? It's fine. How are you today? Correct. So the input is text and the output is text. But in fact, the machine learning know nothing about the text. We convert my text as the input into array of numbers, of values, and the output also will be an array of values. And after that, in the input, I will change each word by an index, and in the output, I will change each index by a word. So in this case, we are getting text in, text out, right? But inside, in the processing part, it's numbers. But in case of fuzzy logic system, no, it's not numbers. We are working with words. So all numbers, we need to convert all those numbers into words. And we will make some processing using fuzzy rules, make decisions. So the decision also will be a word, for example. And after that, in the output, we need to convert this word into a number again. So at the input, we have something we call it fuzzification. And in the output, we have something we call it defuzzification. We fuzzify here, and we defuzzify in the other side. And in the middle, we will have a rule base. This rule base will contain all my rules. My rules will be very simple. It will be a set of if-then rules. If something, then something else. If condition, then action. So this is the rules. If condition, this action. If temperature is hot, then clothes is light, right? So we have conditions, we have actions. So those rules will create the mapping between inputs and outputs. When we apply those rules to the inputs, some rules will be fired, which means some rules will be active. The active rules will go to something called inference engine, and this inference engine will try to use those rules like in a washing machine. In fact, it will just try to, like in a washing machine, it will try to use it like this to make some decision, right? So this, I mean, that is it, in fact. So fuzzy logic system, we are working with words. We are not working with numbers. All numbers will be converted into words. If you have temperature, we need to convert it into a word, maybe hot, medium, cold, for example, if it's height. So it will be tall, medium, short, right? If we are talking about people in the classroom, some people are tall, some people are very tall, some people are short, some people are very short, some people are medium, correct? Fast, some car is slow, fast, medium, very fast, very slow, correct? Expensive, cheap, right? So we will, it's like our daily language, in fact. So when we are building this expert system, we are using our daily language. We are using the language which we use in each daily life to build a system, and therefore they call it white box, because when we look into it, right, you will understand all things. You will understand. You can just pick in rule, just open one rule. You will understand what is the function of this rule, in fact, because it's not magic. Right? It's similar to if temperature is hot or temperature is very hot, clothes is very light, right? So basic, simple. So I will understand. So the basic, the piece of information in my fuzzy logic system, it will be each single rule, right? And each single rule, it will explain itself by itself, right? It's easy to understand. And the inference process, it's a simple. I have some inputs, and we'll apply those rules into those inputs. Some of those rules will be fired, and we will generate some output, right? The input output, it will be words. So I need to fuzzify in the input and defuzzify in the output, and that is it. So in fact, next week we will stop here this week. So now you have access to this Olfetti faces. Please go to this Olfetti faces and now start working on it. We can meet again after 1 hour, for example. At now it's 12. We can meet at 1, for example, and we can discuss in this problem. So you will have 1 hour now to work in this Olfetti problem, and I will not talk again more about fuzzy logic system today. It's enough for this slides today. I will upload it to Blackboard, so you can read it before next week again. And the next week we will start building our system piece by piece, right? So we will build it function by function. And at the end, we will have a system where we will apply it to a benchmark problem. We have a very nice benchmark problem in chapter 13. This problem is from a bank. So we will apply it to this problem. We will build our system and we will apply it to this benchmark problem from chapter 13. And maybe we can take 2 weeks, for example, 2 weeks, it will be okay, right? 2-3 weeks, maybe 3 weeks is too much, maybe 2 weeks this week, and the next 2 weeks, for example, for finishing this expert system part and testing it. Yes. So any question for today? Any question, Magnus, and the rest? So now you have access to this all 50 faces. Now you need to go to this file, and at 1 I will disappear for 1 hour because we have department meeting. So I will disappear for 1 hour, and at 1 we can meet again and we can discuss if you have any questions in your coding for machine learning part. But for today, we will it's enough for this introduction to expert system. Please try to read this slide. I will upload it to Blackboard very soon, and we will meet again at 1 if you have any questions. So I will be online until 2:15. From 1 to 2:15, I will be online. If you have any questions for your machine learning code for all 50, you are free. You can go for all 50. You can go for any other data set. The most important thing for me is to use the same pipeline and to apply it to any data set. It's okay. So even if you want to go for MNest, we solved it already. So it's no problem. I mean, the most important for me is to apply this pipeline to a data set from A to Z, right? From deep loading your data until you make decisions and check the performance of your system. Yeah. Okay, thank you very much for today. And please let me know if you have any questions.